Dear students, welcome to the next session of the course Analog Integrated Circuits, dealing with the topics Analog Multiplier and Voltage Controlled Oscillator or VCO. These two topics form part of Module 5 of Analog Integrated Circuits. What is an analog multiplier? An analog multiplier can be defined as a circuit whose output is proportional to the product of input voltages Vx and Vy. That is, V output is equal to K into Vx Vy, where K is called proportionality constant or scaling factor. Normally, the value of K is equal to 1 by 10 and the unit is volt inverse. The shown figure can be the block diagram of an analog multiplier with two inputs Vx and Vy and output Vo, which is proportional to the product of Vx and Vy. Let us learn about certain characteristics of multipliers. First one is accuracy. By accuracy we mean the deviation of the actual output of the multiplier from its expected output when the inputs are within the permissible range. That is, how much the actual output varies from the expected ideal output. Next is linearity. The term linearity comes into view when one of the inputs is a constant. That is, you keep one input to the multiplier constant and vary the other input. So when you multiply, you expect the output to be on a straight line. So how much the actual output varies from this expected straight line output is given by linearity. So we measure linearity by keeping one input constant of the multiplier, and as I said, it represents the maximum deviation of the output from what is expected, that is the straight line output. This is the graph transfer curve. Vx, which is the changing input voltage, is plotted along the x-axis and the output is plotted along y-axis. The other input Vy is kept a constant. So you expect the output to be on this straight line, but you get a curve like this. So this maximum deviation is the linearity error. Maximum deviation of the actual output from the straight line ideal expected output is called linearity error. Next is squaring mode accuracy. To find squaring mode accuracy, both the inputs are given the same value. That is, the inputs are connected together and given the same value. So the output would be the proportionality constant K into the square of the input values. You expect the output to be on this dotted straight line, which is the ideal square law output, but the actual output of the multiplier when both the inputs are same would be like this. So the squaring mode accuracy is measured by the maximum deviation between the actual output and the expected output. Next multiplier characteristic is quadrant. Quadrant defines the polarity which can be provided to the input. What do you mean by polarity? Whether the input can be positive or negative or both. If a multiplier is said to be a single quadrant multiplier, the input can have only one polarity, that is either positive or negative, and both the inputs should be of the same polarity. If the multiplier is a two quadrant multiplier, then one input should have only a single polarity, that is either positive or negative, and the other input can have both the polarities, that is it can be positive or negative. In the case of a four quadrant multiplier, both the inputs can take any values positive or negative. So a single quadrant multiplier, both the inputs can have only a single polarity and it should be the same. For a two quadrant multiplier, one input can have only a single polarity and the other input can be positive as well as negative. For a four quadrant multiplier, both the inputs can be positive or negative. So these are some of the important multiplier characteristics. Now let us see what are the different ways of implementing a multiplier. First one is logarithmic summing. In this, we take logarithm of both the inputs and add them and take the anti-logarithm of that to obtain the product. So the inputs are converted to their logarithmic equivalents and added. When we add logarithm of Vx plus logarithm of Vy, we will be getting logarithm of Vx into Vy. So when we take anti-logarithm of this, we get the product Vx into Vy. This is the circuit. Vx and Vy are supplied to logarithmic amplifiers and its logarithm is obtained. It is added. That is, here we get logarithm of Vx into Vy. When it is provided to an anti-logarithmic amplifier, we get the output as Vx Vy. So this is a simple technique, but it has got several disadvantages. First one is the accuracy is less, and this is highly temperature unstable. Also, the inputs should be positive. That is, the operation of this multiplier is restricted to only one quadrant. Another technique of implementing multiplier is pulse height / width modulation. In this, we have a train of pulses whose height is proportional to one input voltage and width is proportional to the other input voltage. That is, height of the pulse train or its amplitude is made proportional to one input voltage and width of the pulse is made proportional to the second input voltage. Let A be the amplitude or height of the pulse train. It is made proportional to the input voltage Vx. If T is the width of the pulse train, it is made proportional to the input voltage Vy. Let us see the pulse train. This is the pulse train. The height A is proportional to one input voltage Vx and the width T is proportional to the second input voltage Vy. Now this particular pulse train is fed to an integrator. The output of the integrator is proportional to the area of this pulse train, A into T. So what is the area of pulse train? When we substitute A and T in terms of Vx and Vy, we get output of the integrator as Vx Vy by Kx Ky. That is, the output of integrator is proportional to the product of the inputs. This technique is called a pulse height / width modulation technique for implementing multipliers. Next technique is an emitter coupled transistor pair. The circuit is shown. This is the emitter coupled transistor pair. The emitters are joined together and IEE is the bias current for this emitter coupled pair. So when you learn the large signal analysis of BJT differential pair, you will derive the equation of IC1 and IC2 like this. IC1 is equal to the emitter current IEE divided by 1 plus e raised to minus the voltage applied to the base minus V1 by the thermal voltage Vt. Now when you write IC2, that is equal to IEE by 1 plus e raised to minus of the input voltage applied, that is to the base of the transistor Q2 we are applying negative voltage. So minus of minus V1, which would be plus V1 divided by the thermal voltage Vt. For the time being, you just remember these two equations. We will derive this while performing the large signal analysis. So this is IC1 and IC2. Now we are finding out the difference between IC1 and IC2. Delta IC equal to IC1 minus IC2. We substitute the equation. Now if you see, this can be expressed in the terms of hyperbolic tan function. This can be expressed as IEE into tan h of V1 by 2 Vt. This 1 by 1 plus e raised to minus V1 by Vt minus 1 by 1 plus e raised to V1 by Vt can be expressed in terms of the hyperbolic tangent function like this. One another property of tan h of x is when x value is very small, tan h of x can be approximated to x. That is, tan h of x can be expanded as x plus x cube by 2 factorial plus etc. So when x value is very small, tan h of x can be approximately equal to x. So we are using that property here. That is, we are making V1 very much less than 2 Vt. So tan h of V1 by 2 Vt will be approximately equal to V1 by 2 Vt. And when you substitute, that delta IC will be approximately equal to IEE into V1 by 2 Vt. Let that be equation 1. So this is an emitter coupled transistor pair. Here we have only one input. For a multiplier, we need to provide one more input. Let us see how that is done. Now an additional circuitry is being added to provide the second input. the second input is provided in such a way that this input V2 is proportional to the bias current of the emitter coupled pair IEE. This additional circuit is added in such a way that V2, not exactly V2, V2 minus VBE is proportional to the input bias current IEE. So as I said, we are providing the second input voltage using an additional circuit in such a way that V2 minus VBE is proportional to the bias current of the emitter coupled pair IEE. KO is the proportionality constant. Now we are substituting this value of IEE in equation 1 in the previous slide. Then we get delta IC equal to KO into V1 into V2 minus VBE by 2VT. So we saw that delta IC is proportional to the product of V1 and V2. Now if you have a current to voltage converter here where you get delta IC, you can obtain a voltage which is proportional to the product of V1 and V2 by converting delta IC to its corresponding voltage value. So that is how this is done. We have an emitter coupled transistor pair. Input is provided. The second input is provided using an additional circuitry. We saw that the differential output voltage delta IC is proportional to the product of V1 and V2. By using a current to voltage converter, we can convert this delta IC to its appropriate voltage, which again would be proportional to the product of V1 and V2. But there are certain limitations to this technique. The first one is that we are not multiplying V1 by V2. We are actually multiplying V1 to the difference of V2 and VBE. That is, the input V2 is always offset by a value VBE. So V2 has to be greater than VBE and hence it has to be positive. That is, this entire multiplier can be used only as a 2-quadrant multiplier. Why? Because V2 has to be positive. We said there is a limitation. V2 has to be positive. V1 can be positive or negative. So this entire multiplier can be used to implement only a 2-quadrant multiplier. In order to overcome this limitation, we go for another technique called a Gilbert multiplier cell. A Gilbert multiplier cell is actually a modification of the emitter coupled transistor pair. In a Gilbert multiplier cell, we have two cross coupled emitter coupled pair in series with another emitter coupled pair. So this is one emitter coupled pair. This is the another emitter coupled pair. These two are cross coupled. So this is the two cross coupled emitter coupled pair. They are in series with this emitter coupled pair. So we saw that the Gilbert multiplier cell is a modification of the previous circuit wherein we have two cross coupled emitter coupled pairs in series with another emitter coupled pair. Now the current directions are marked. We will write the equations of all these currents IC3, IC4, IC5, IC6, IC1 and IC2 in terms of the threshold voltage and voltages as in the previous case. So how will we write IC3? For this emitter coupled pair, the bias current is IC1. The current flowing through this portion is IC1. So IC3 can be written as IC1 divided by 1 plus e raised to minus voltage, that is minus V1 by Vt. IC4 is IC1 divided by 1 plus e raised to minus of minus V1, that is plus V1 by Vt. Similarly, we write the equations for IC5 and IC6. Here the bias current is IC2. So IC5 and IC6 can be written like this. Now we write the equations for IC1 and IC2. For this emitter coupled pair, the bias current is IEE and the voltage is V2. So these are the equations for IC3, IC4, IC5, IC6 and IC1 and IC2. Now let us substitute the value of IC1 and IC2 with the respective equations in these four equations. That is, we are substituting the values of IC1 and IC2 in the equations for IC3, IC4, IC5 and IC6. We get these four equations. Here instead of IC1 we are substituting this equation, and here instead of IC2 we are substituting these equations. We get these four equations. Now what is the differential output current? It is IL1 minus IL2. Let us denote it by delta I. Delta I is equal to IL1 minus IL2. Here we can see that IL1 is split as IC3 and IC5. So IL1 can be written as IC3 plus IC5 minus IL2 can be written as IC4 plus IC6. Here we can see that IL2 is split as IC4 and IC6. So we can rewrite this as IC3 plus IC5 minus IC4 plus IC6. We are just rearranging this equation as IC3 minus IC6 minus IC4 minus IC5. And in this equation, we are substituting these equations for IC3, IC4, IC5 and IC6. We are substituting those current equations and converting it to the hyperbolic tangent function. So we get delta I. We got delta I as IC3 minus IC6 minus IC4 minus IC5. We substituted these equations and converted it to hyperbolic tan function. We got delta I is equal to IEE into tan h of V1 by 2 Vt into tan h of V2 by 2 Vt. Now as in the previous case, we are assuming V1 and V2 to be very much less than Vt. So this can be rewritten as delta I is equal to IEE into V1 by 2 Vt into V2 by 2 Vt. So we saw that the differential output current is proportional to the product of input voltages V1 and V2. That is delta I is proportional to the product of V1 and V2. By using a current to voltage converter, this delta I can be converted to its appropriate voltage value. So there is no, the input voltage V2 is not offset by VE, and so there is no limitation of V2 to be positive. So this Gilbert multiplier cell can be used to implement a 4-quadrant multiplier. So we learned what an analog multiplier is. We learned about the different techniques of implementing an analog multiplier. This analog multiplier is available as integrated circuits also, which consist of op-amps and other components in that IC. So let us see one of those ICs, which is AD633. So we know what an analog multiplier is. As I said, it is available as integrated circuits. One popular such analog multiplier IC is AD633. So this is the pin diagram of AD633. We can see that at pins 1 and 2 we are applying two inputs X1 and X2. At pins 3 and 4 we are applying two inputs Y1 and Y2. These are being fed to op-amps, that is differential amplifiers. The difference is being multiplied, that is X1 minus X2 into, here we get Y1 minus Y2, that is being multiplied. Now that is being given to an adder, which is being provided with another input Z, and that is being provided to a voltage follower. So we get the output at W. So pin numbers 1, 2, 3, 4 and 6 are the inputs, W is the output, and 5 and 8 are used to provide the supply voltages. So we need not always provide all these inputs. Depending upon our application, we can ground X2, Y2 as well as Z. So when we ground X2, Y2 and Z, here we will get only what? X1 into Y1 plus Z is 0. So X1 into Y1 plus 0, that would be obtained at W. So depending upon our application, we can either provide all these inputs or we can ground certain inputs. So let us look at some of the characteristics of AD633 multiplier. This can be used as a 4-quadrant multiplier. It has got a high input impedance. Therefore, it does not load the source. Supply voltage, that is plus minus Vs, can range from plus minus 8 volt to plus minus 18 volt. The input signal range can be plus minus 10 volt. We are imposing this limitation so that this IC does not go to saturation. And as I said, what is the overall transfer function? W is equal to, this is a differential amplifier. Here we get x1 minus x2. Here we get y1 minus y2, and that is multiplied. So x1 minus x2 into y1 minus y2 by 10. There is always a scaling factor. Then plus Z. So W is equal to x1 minus x2 into y1 minus y2 by the scaling factor. There is a scaling factor, you can see that here, by 10 plus Z. So as I said, depending upon our application, we can ground some of these inputs. So this is the transfer characteristic of a 4-quadrant multiplier. The output is plotted along y-axis and input is plotted along the x-axis. We can see that the input is plotted for both positive and negative values of Vx as well as positive and negative values of Vy. All these are negative values of Vy. This is Vy is 0 and these are positive values. So depending upon whether Vx and Vy are positive or negative or both, the output will lie on each of these quadrants. Here for each of these lines, we are taking a constant value of Vy. That is why we are getting a straight line output. That is, Vx is varying but Vy is a constant for each of these curves. So this is the transfer characteristic of a 4-quadrant multiplier. Let us see some of the applications of AD633 multiplier IC. First one, it can be used as a voltage squarer. How will you use it as a voltage squarer? Just by shorting the inputs and giving a single value. The inputs are shorted together and given a single value. So obviously the output would be the square of the input. And as I said, the inputs can be positive or negative between 0 and 10 volt. A limitation is imposed so that the IC does not go to saturation. Next, AD633 IC can also be used as a frequency doubler. So again the inputs x1 and y1 are shorted together and provided with the input and we take the output. So let the input provided be AV sin 2 pi ft. So what will be the output? AV sin 2 pi ft into AV sin 2 pi ft by the scaling factor 10. That is equal to sin squared theta is equal to 1 minus cos 2 theta. So this becomes AV squared into 1 minus cos 4 pi ft, the whole divided by 10. So we can see that there is a DC value AV squared into 1 by 10. That DC value can be removed by placing a capacitor at the output. If we remove that, we will only get an output whose frequency is double, that is cos 4 pi ft, double of the input frequency. Frequency of the input is 2 pi ft, but we get 4 pi ft at the output. So we saw that AD633 can be used as a frequency doubler. Next is voltage divider and square rooter. This is the circuit for using AD633 as a voltage divider as well as square rooter. First we will see voltage divider. So you have a numerator V nu and V denominator. So we expect an output to be V numerator divided by V denominator. We can see an op-amp whose output is fed to one of the inputs of the AD633. The other input of AD633 is the V denominator. So what is VO, output of the multiplier? Scaling factor K into VOA, one input into V denominator. We have marked two currents here, I1 and I2. There is no current into the op-amp because of the high input impedance. So applying Kirchhoff's current law at the node A, we get I1 plus I2 equal to 0. Now we are substituting I1 and I2 in terms of voltages and resistors. The node A is at virtual ground. We can say that the node A is at virtual ground. So the voltage at this point is 0. So what will be current I1? V numerator minus 0 by R. Plus what is current I2? VO minus 0 by R. So when we sum, we get V numerator by R plus VO by R is equal to 0. And we get VO is equal to minus V numerator. Now we are substituting this value in the first equation here. We get minus V numerator is equal to K into VOA into V denominator. So now what will we get? VOA, that is the output of op-amp, is equal to minus V numerator by K V denominator. That is, if we take the output of the circuit from this point, it can be used as a voltage divider, V numerator by V denominator, which is scaled by 1 by K. Now, the same circuit can be used as a square rooter if both the inputs to the multiplier is the op-amp output. That is, X1 and Y2 are both given VOA as the input. So let us assume that the numerator value Vi is the input to be squared. V numerator is equal to Vi and X1 and Y2 both is equal to VOA. So we are just substituting VOA is equal to, in this equation we are substituting the changed values, that is VOA equal to minus V numerator. What is V numerator now? It is Vi, the input that needs to be squared, divided by K into V denominator. V denominator is being provided the output of this op-amp, VOA. So by K into VOA. So we get VOA squared is equal to minus Vi by K, or VOA is equal to square root of modulus of Vi by K. So if we are connecting the circuit in such a way that both the inputs to the multiplier is the op-amp output, we can use the circuit as a square rooter. So this is how it works. Next application is phase angle detector. So this is AD633 multiplier. We are providing a VY input to the terminal Y1 and a phase shifted input to X1. That is, Vy is Vyp into sin 2 pi ft. Vx is Vxp into sin 2 pi ft plus theta. So we are trying to find out theta here. So what is the output of this multiplier? V output is equal to Vx into Vy by the scaling factor K. We are just multiplying Vxp into Vyp into sin 2 pi ft into sin 2 pi ft plus theta by K. So what is sin A into sin B? The formula is sin A into sin B equal to 1 by 2 the whole into cos A minus B minus cos A plus B. We are using that equation here and we get VO is equal to Vxp into Vyp into cos A minus B, that would be cos theta, minus cos A plus B 4 pi ft plus theta, the whole divided by 2k. There is a 1 by 2 cos A minus B, so that 2 comes here. So normally the value of k is 10. Substituting, we get V output is equal to Vxp into Vyp into cos theta minus cos 4 pi ft plus theta by 20. So again here we can see there is a DC component which is equal to Vxp into Vyp into cos theta, the whole divided by 20. Now we need to find out theta. So let us provide two inputs in such a way that Vxp into Vyp equal to 20. So we get the DC component of output VODC as cos theta. If we place a DC voltmeter at the output which can measure between 0 to 1 volt, we can directly use this to measure the value of cos theta in terms of voltage. Why do we use a voltmeter to measure between 0 and 1 volt? Because the maximum value of cos theta is 1 volt. Okay. So we are at the input we are giving two phase shifted inputs. We get the output like this, and we are placing a which has a DC component Vxp into Vyp into cos theta by 20. We provide two inputs in such a way that Vxp into Vyp is cos 20. So we get the DC component as cos theta, which can be directly measured using a DC voltmeter placed at the output. In that way we can find out the phase angle theta. So that's all about analog multipliers. we learned what is a multiplier. We learned the different techniques to implement a multiplier. Then we learned about a multiplier IC. Also we learned about multiplier characteristics. Now we'll go to the next part, which is voltage controlled oscillator or VCO. So what is an oscillator? An oscillator is any circuit which can generate a waveform without any input signal. A voltage controlled oscillator generates a waveform whose frequency is controlled by a control voltage VC. We can also call VC as a modulating voltage. So frequency FO of the oscillator is proportional to VC. FO is equal to K into VC, where K is the sensitivity of the voltage controlled oscillator. So voltage controlled oscillator is an oscillator which generates an output signal whose frequency is controlled by another control voltage or modulating signal VC. And we defined the term K, which is the sensitivity of the voltage controlled oscillator. A voltage controlled oscillator is of two types: grounded capacitor voltage controlled oscillator and emitter coupled voltage controlled oscillator. We will learn about grounded capacitor VCO. So let us see how that works. This is the basic circuit of a grounded capacitor VCO. We can see there is a Schmitt trigger. This is an inverting Schmitt trigger. There is a capacitor. There are two current sources, I1 and I2. A Schmitt trigger controls a switch. It has got two positions, 1 and 2. And this is the modulating voltage VC, or the output frequency is controlled by this voltage VC. So let us see how this works. Let us assume that the Schmitt trigger is currently, the output of the Schmitt trigger is currently high and the position of the switch is in position, the switch is in position 1. And assume that currently the voltage across the capacitor VC is 0. So we said the position of the switch is at 1. Now the capacitor starts charging. This is closed. The position is at 1. So the capacitor starts charging through the current source I1. The capacitor keeps on charging. So this Schmitt trigger has got a UTP and an LTP. And I said this is an inverting Schmitt trigger. So when the voltage of the capacitor, which is provided to the inverting terminal, becomes greater than the UTP, that is, the voltage at the inverting terminal becomes greater than the voltage at the non-inverting terminal, the Schmitt trigger output switches to low. So the capacitor keeps on charging through the constant current source I1. At a point, the voltage across the capacitor reaches UTP and Schmitt trigger output switches to low. When Schmitt trigger output switches to low, what happens? The switch shifts to position 2. Now it shifts to position 2. Now the capacitor starts discharging through the current source I2. The capacitor is charged. Now this is a current sink. The capacitor starts discharging through I2. And we have made I1 and I2 equal by means of this. I1 and I2 is controlled by this VC, modulating voltage VC, and it is kept equal. I1 and I2 is equal. So what does that imply? It implies that the charging time and the discharging time of the capacitor is equal. So the capacitor is charged through this current source I1 and it discharges through this current source I2. I1 and I2 is equal. So the charging and discharging time of the capacitor is equal. Also, we need to mention that I1 and I2 is a constant current source, that it is not variable. It is a constant current source. So the charging of the capacitor would be linear. It is not exponential as is the normal case. Since the current source is constant, the charging and discharging of the capacitor is linear. And also since I1 and I2 are equal, the charging and discharging time of the capacitor is same. So let us see how. Let us see how capacitor charges linearly. What is the equation for voltage across a capacitor? VC is equal to 1 by C into integral IT dt. So we said in this case our current source is constant, that it is not varying with time. So how can we write VC? VC equal to 1 by C integral constant I into dt, or we can write Vc is equal to I into t by c. I is constant, it is not varying with time. So we saw that Vc is proportional to t, the time. That means the voltage across the capacitor varies linearly with time. It is not exponential, it is linear. So that is what you mean by when the current source is constant, the capacitor charges linearly. Now this is the output of the Schmitt trigger and the capacitor of the previous circuit. The output of the Schmitt trigger and the capacitor. Let the output of the Schmitt trigger vary between 0 and VCC. And the capacitor, as I said, it charges linearly and discharges linearly because the current source is constant. So we have got a triangular waveform and as the capacitor output. And we said that since I1 and I2 is equal, the charging time and the discharging time is same. That is, it is equal to t by 2. So we get a triangular waveform. So initially the capacitor starts charging from 0 and then it charges and it reaches VUTP. It starts discharging. When the capacitor discharges and reaches VLTP, what happens? The Schmitt trigger switches to high. See, at this point the Schmitt trigger switches to high. Again the capacitor starts charging. So now here in this phase it starts charging from VLTP and not from 0. So this is the initial state. The capacitor starts charging from 0 and here the capacitor, further the capacitor starts charging only from VLTP to VUTP. That is the steady state. So let I1 equal to I2 equal to I. We know the charging and discharging time is equal. For a capacitor, Q is equal to CV. That is dQ by dt equal to C into dV by dt. dQ by dt is I, the current through the capacitor. So I is equal to C into dV by dt. So what is dV by dt for this capacitor? The capacitor varies from VLTP to VUTP, correct? In the steady state. So dV is VUTP minus VLTP divided by time. How much time does it take? It takes only t by 2, half the period, divided by t by 2. That is I is equal to 2C into VUTP minus VLTP by t. Or the time period t is equal to 2C into VUTP minus VLTP by I. That is, what is the frequency? Frequency is I by 2C VUTP minus VLTP. Frequency is proportional to the current through the capacitor I, and that current source is managed by this modulating voltage source VC. So ultimately the frequency is proportional to VC. So we saw that in the V0, the frequency of the output waveform can be changed by changing the control voltage VC. So this is how it is proved. Here we are proving how the capacitor charging is linear if the current is constant. And here we are proving how the frequency of output of a VCO is proportional to or is affected by the modulating control voltage VC. Okay, so now we learned what is a VCO. We learned that it is an oscillator whose output frequency can be controlled by a modulating signal or a control voltage VC. Now we learned one such VCO integrated circuit or IC, which is NE/SC566. So this is the internal circuit diagram of NE/SC566. As we studied the general working of a grounded capacitor VCO, here we have a constant current source / sink. Constant. It is a constant current source, which means that the capacitor charging would be linear. There is an inverting Schmitt trigger. Then you have two buffers. The supply voltage is given to pin number 8. The modulating input signal is given to pin number 6. There is a pin number 5. Sorry, the same voltage is available at pin number 6 also through some internal circuitry. Then a capacitor is given at pin number 7. The outputs are taken from pin number 4 and pin number 3. the output, the triangular waveform is taken from pin number 4 and the output of the Schmitt trigger is inverted and taken from pin number 3. So let us see how this works. In this particular IC, the Schmitt trigger is designed in such a way that the output of the Schmitt trigger does not vary from minus Vsat to plus Vsat, but it varies between VCC and half of VCC, 0.5 VCC. VCC is the supply voltage given. So the output of the Schmitt trigger varies between VCC and minus VCC. So this capacitor C1 is charged and discharged by this constant current source / sink. As I said, the control voltage which controls the frequency of the output signal is applied to pin number 5. The same voltage is available at pin number 6 also through some internal circuitry. We have two resistors RA and RB which are equal in value. So what happens when this is the feedback? What is the value at the non-inverting terminal? This is a potential divider and RA and RB values are same. So we said the Schmitt trigger output varies between VCC and 0.5 VCC. So when the Schmitt trigger output is VCC, the voltage at this terminal is 0.5 VCC by the application of this potential divider. RA and RB are equal. And when the Schmitt trigger output is 0.5 VCC, the voltage at the non-inverting terminal is half of that is 0.25 VCC. Try to find out how. This is the potential divider and RA and RB are equal. So the voltage at this terminal would be half the voltage at this terminal. So since the Schmitt trigger output varies between VCC and 0.5 VCC, the voltage at the non-inverting terminal varies between 0.5 VCC and 0.25 VCC. Now let us consider the case where a capacitor is charged by this constant current source. This is an inverting Schmitt trigger. The capacitor keeps on charging and reaches a value of 0.5 VCC. So what happens? Suddenly this Schmitt trigger output becomes low, and that is the output of the Schmitt trigger is 0.5 VCC. Initially it was high, the capacitor was charging. Now the capacitor, so when the output of the Schmitt trigger is high, what is the voltage at this terminal? It is 0.5 VCC. Capacitor keeps on charging by this constant current source. It reached the value of 0.5 VCC. So suddenly the Schmitt trigger output became low. That is, the Schmitt trigger output becomes 0.5 VCC. So this affects the current source and now the capacitor starts discharging. When the Schmitt trigger output becomes low, the capacitor starts discharging. The capacitor keeps on discharging and reaches a value of 0.25 VCC. So initially the Schmitt trigger output was high, that is, it was VCC. At that time the voltage at this terminal was 0.5 VCC. The capacitor keeps on charging and reached 0.5 VCC. The output of the Schmitt trigger switched to low, that is, the output of the Schmitt trigger became 0.5 VCC. At that point, the voltage at this terminal, non-inverting terminal, is 0.25 VCC. When the output of the Schmitt trigger became low, the capacitor started discharging. The capacitor discharges and reaches 0.25 VCC. That is, now the voltage at both these terminals are same. Suddenly, the Schmitt trigger switches to high. That is, it becomes VCC. And again, the capacitor starts charging. So, this process goes on. Now, we know that the current source, constant current source and sink are the same value. So the capacitor charges and discharges for the same amount of time. As a result of that, a triangular waveform is obtained across the capacitor at pin number 4. The current source and sink is of the same value. So the capacitor charges and discharges for the same amount of time. And this is a constant current source. So we get a triangular waveform, and that is obtained at pin number 4. And the output of the Schmitt trigger is inverted and obtained at pin number 3. So let us try to calculate the frequency of the output voltage. So this is the triangular output obtained at pin number 4, and this is the Schmitt trigger output obtained at pin number 3. the triangular output varies between 0.25 VCC and 0.5 VCC, and the Schmitt-Trigger output varies between 0.5 VCC and VCC. So we are trying to find out the frequency. For a capacitor, Q is equal to CV, dQ by dt, that is I, is equal to C into dV by dt. So what is that? dV by dt or delta V by delta T is I by C1. Here in this case, C is C1. So what is delta V by delta T? Delta V is the capacitor value changes from 0.25 VCC to 0.5 VCC. So what is the change? 0.5 VCC minus 0.25 VCC, that is 0.25 VCC, and let this time taken be delta T for this change. Half the time period be small delta T. So delta V by delta T equal to 0.25 VCC by delta T, that is equal to I by C1. So what is delta T now? Half the time period of this triangular wave, 0.25 VCC into C1 by I. So the total time period of the triangular wave is 2 times delta T, that is 0.5 VCC by I. So what is the frequency of this triangular wave? The reciprocal of time period, I by 0.5 VCC into C1. So what is I? Now we need to find out I. I is equal to VCC minus VC, the whole divided by R1. How is that? Therefore, the frequency F is equal to, we are substituting the value of I, VC, 2 into VCC minus VC by R1 C1 VCC. F is equal to, we are substituting this value of I, VCC minus VC by R1 C1 VCC. So now we saw that the frequency is dependent on the modulating voltage VC. Now we can see how the frequency is controlled by the modulating voltage or control voltage VC, and this is the equation for frequency. So how did the equation for current I become VCC minus VC by R1? I said that the modulating input voltage VC, which is applied at pin number 5, is also available at pin number 6 due to some internal circuitry. So the current becomes, that is the voltage at this point is VC, modulating input voltage VC. So the current becomes VCC minus VC by R1. So that is how we derived the equation for frequency of the VCO IC 566. So we saw that the frequency of the IC is dependent on the modulating input voltage VC. So another important term is the voltage to frequency conversion factor. That is another important term that is associated with this IC 566. It is denoted by kV and it is defined as delta F by delta VC. So that is the change in the frequency of the output voltage to corresponding change in the control voltage. That is, there is some change in the control voltage delta VC and it provides some change in the frequency, output frequency delta F. So let us try to derive an equation for that. Let the initial frequency be F when the control voltage was VC, and let F dash be the new frequency. So what is delta F change in frequency equal to F dash minus F, and VC, that is the control voltage, changes by delta VC to achieve this change in the frequency. So from the previous slide we have derived the expression for frequency as 2 into VCC minus VC by R1 C1 VCC. We are applying that here. So what is F dash? F dash is the frequency when the control voltage is VC minus delta VC. So we are applying that equation here. F dash is equal to 2 into VCC minus VC minus delta VC, the whole divided by R1 C1 VCC. VCC. And what is F? F is the frequency when the control voltage was VC. So we are just subtracting F dash minus F to obtain delta F. Delta F is equal to 2 into delta VC by R1 C1 VCC. And from this we are trying to find out delta VC. Delta VC equal to delta F into R1 C1 VCC by 2. Now one thing that you have to keep in mind is when no modulating voltage is applied, that is there is no voltage at pin number 5. We are not applying any modulating voltage. The value of voltage at that pin becomes 7 by 8 VCC. This is due to the internal circuitry of the IC. So when we do not apply a modulating voltage at pin number 5, the value of VC becomes 7 by 8 VCC. So we are applying this value of VC in the equation for F. What is the equation for F? F is equal to 2 into VCC minus VC by R1 C1 VCC. We are applying this value of VCC here and we get F is equal to 0.25 divided by R1 C1. Now in this equation F is equal to 0.21 divided by R1 C1. Instead of R1 C1 we are trying to derive an equation for R1 C1 from this. Delta VC equal to delta F into R1 C1 VCC by 2. So from this equation what is R1 C1? R1 C1 equal to 2 into delta V divided by delta F VCC. So here we are applying that value for R1 C1. F is equal to 0.25 by R1 C1. Instead of R1 C1, we are applying 2 into delta VC by delta F VCC. So we get kV is equal to delta F by delta VC. When we substitute, we get kV is equal to 8F by VCC. So a 2 is missing here. There should be a 2 here. F is equal to 0.25 into delta F into VCC by 2 delta VC. So when we try to find out delta F by delta VC from this equation, we get delta F by delta VC, which is the voltage to frequency conversion factor kV, that is equal to 8F by VCC. So this is the equation for kV, or the voltage to frequency conversion factor. How did we find that out? Initially let the frequency be F and the control modulating voltage be VC. Now let the modulating voltage be changed to VC minus delta VC. Then the frequency changes to F dash. So the change in frequency delta F is F dash minus F. We have earlier found out the equation for the frequency F. We are substituting the values of Fc minus delta Vc to find out the expression for F dash. Then we subtracted F dash minus F to obtain the expression for delta F. From this we found out that R1 C1 is equal to 2 into delta V by delta F into VCC, and delta Vc is equal to delta F into R1 C1 into VCC by 2. Now if no modulating voltage is applied to pin number 5, by the internal circuitry, the voltage at pin number 5 becomes 7 by 8 VCC. We are applying that here in the equation for F, and then we get F is equal to 0.25 by R1 C1. We are finding out an equation for R1 C1 from this equation. R1 C1 becomes delta Vc into 2 divided by delta F VCC. We are substituting that here. A 2 is missing here. Please add that 2. So F becomes 0.25 into delta F into VCC by 2 delta Vc. When we find out delta F by delta Vc from this equation, we get kV, that is the voltage to frequency conversion factor kV, equal to delta F by delta Vc equal to 8F by VCC. So this is a very important term for the VCO IC. So in this session we have learned about analog multipliers, how it is implemented, some of the characteristics of analog multipliers, one analog multiplier IC. Then we learned what is a voltage controlled oscillator, how a general grounded capacitor voltage controlled oscillator works. Then we learned a voltage controlled oscillator IC, how it works. we found out how the frequency is dependent on the modulating frequency. Then we also learned a very important term, which is the voltage to frequency conversion factor. Thank you.